Hi, today we're going to talk about, well, on the slide, as it says, balancing chemical equations. So to get us into this, obviously we just saw the video about what happens on a scale when you burn a piece of steel wool. And if you're unfamiliar, burning steel wool has this characteristic glow color to it. There are a number of people who do long exposure photography, which honestly it comes out looking amazing. Um, and now that I'm actually staring at it, a little bit like the special effects they use in Doctor Strange. Wonder if you could step through it. Anyway, the question is, why is the mass changing? How do we represent that chemically? This is our first jab into actually describing how chemistry happens with symbols and measuring. So first, let's talk about the symbols. We're now going to talk about, moving forward, chemical equations. This is our textual, symbolic representation of chemistry happening. There's a couple of things that we need to point out first. The left side of any equation is called the reactants. The right side is the products. The right side and the left side are separated by an arrow, which, as it says here, verbally means react to produce. Sometimes that is represented by the word yields. A plus B yields C. On the right side, as I said, you have your products. You're going to see a lot of times ionic charges and phases. So those are things we've seen before, sometimes referred to as physical states. The plus here does mean and. It doesn't mean positive. That's these pluses here that I'm putting in boxes. This does suggest that in the case here, the reactants and the products are both mixtures. That's fine. Sometimes you'll see something in this area here on top of the arrow. You'll see a little delta that means I heat it to make sure it happens. Or you'll see some sort of chemical written here, which would mean that there's a catalyst present. We're not going to spend too much time talking about that today. The one thing I do want to mention, though, is that there is a left side and a right side to what we write. This is happening in one container, right? Here, when you see this picture of steel wool burning, it's not like the left side of the steel wool is burning and the right side isn't, or the left side is the reactants and the right side is the products. That's just, we say left and right, but we mean, on the paper. This is happening in a beaker, in a flask, on a table, and it's happening everywhere. It's not just happening on sides. So to talk about specifically what's happening in the burning steel wool, we need to talk about the words, what we observe, and we have to mention some laws in chemistry. In general, when we talk about scientific laws, a lot of people feel like theories, go to college and get a degree and become a law. That's not quite how it happens. The laws say what happens, what we observe to happen. The theories try and suggest why it's happening. So there is a law of conservation of matter that states, quite simply, that the amount of matter that you start with equals the amount of matter that you end with. That is to say, matter cannot be created or destroyed, only modified. It can be transferred. In the case of the burning steel wool, if we were to say what happens in words, iron reacts to become rust. It was rusty. It had this reddish color after it was burnt. We could be a little more specific. Rust is typically iron 3 oxide. So iron reacts to become iron 3 oxide, and we can even start transitioning that into our chemical symbols and write a chemical equation. But what you might notice in the chemical equation, and something we noticed in the actual video, the reaction, is that the mass appeared to change. And it seems like here it appears to be that the products are representing an oxygen that the reactants are not. And I thought it would be good to mention open versus closed systems in this respect. Open versus closed, specifically talking about the vessel in which any process happens. An open system, kind of like an open container, would mean that matter can, enter or leave. This would be a candle. If the candle is burning, there's the ability for matter to enter and leave this container. If we were to close the system, matter cannot enter or leave. And a lot of times, when you put something on top of a candle, you see it burn out. And I feel like a lot of people already know, that's because the oxygen gets consumed. Well, right, and no new oxygen can come in to take its place. So some things that we can talk about here, there's no real way to represent that in a chemical equation. The chemical equations, the conservation has to be shown whether it's an open or a closed container. However, because of an open or a closed container, we can get the appearance that we're violating this law. We never are. But in the case of chemistry, a lot of times an open container will be just as simple as not putting a lid on something, where matter can come in or out. Where that doesn't happen in the case of a closed container. Now that all of this considered, this doesn't really address this conservation. I think we're missing something. Whenever there's this problem where I see an element on one side of the equation that's not on the other, we would probably call this an incomplete reaction. And to address this, we have to consider some of the other chemicals that might be present. I think it might be better to add to this sentence because we did this in air, in a normal atmosphere. So this would be in oxygen. And we probably should represent that in our chemical equation by writing this. This would be more of a complete reaction, where at least we're representing all of the chemicals that participate. That said, I don't know how well you can notice this. This is not what we would consider a balanced equation. This does not still yet show conservation of energy. Specifically talking about the type and number of atoms present on both sides of this arrow. The reactants are showing 1 iron atom, the products are showing 2, and this isn't super helpful. One of the ways we can get around this is by adding what you would call coefficients. Coefficients are big numbers that go out before the chemical, and they do apply to the entire chemical, and they are used to balance this chemical equation. So we're not allowed to go and change any of the subscripts present, right? We're not allowed to just change this Fe2O3 to an FeO3 because this is not the chemical equation for iron 3 oxide. So we can't do that. What we need to do is we need to add coefficients because that tells us the relation between the chemicals, not the relations within the chemicals. So for example, here in a balanced reaction between hydrogen and oxygen to make water, you'll notice that there are some coefficients present. We're not allowed to change the H2. Obviously, hydrogen, diatomic element, that's its chemical formula. O2, oxygen, same deal. Water, H2O. We can't play around with those ratios. Those are set by the chemistry of how those substances exist. But when they interact with each other, we can say, well, when hydrogen and oxygen react, I need 2 hydrogen molecules to react with 1 oxygen molecule to make 2 water molecules. And this 2 would apply to both the hydrogen and the oxygen. Right here we're representing 4 H's and 2 O's. This represents 2 O's, and this represents 4 H's. 2 times 2, of course, being 4. So again, you can see now that we've done that accounting that the conservation of matter is upheld. If you don't see a coefficient, it's always assumed that there's a 1 there. So going back to our iron 3 oxide example, now that we have all our chemicals in and we have a complete reaction but unbalanced, we can start to play this a little bit of this game and try and puzzle out how we can balance it. And the way we do that is just simply by adding coefficients as we need. I like to just start picking an element and counting. So I see 1 iron here, and I see 2 iron here, and I see 2 oxygen here, and I see 3 oxygen here, and so we're clearly not balanced, but I would like to fix that. I think if I put a 2 in front of here, this becomes a 2. So now we're good on the irons, but we're still not good on these oxygens. 2, 3. Well, we can't just put a 2 here because that would mean 4. So let me clean that up. So I think we might have to play a little bit of a least common multiple game. It feels to me like the best way to address this would be, 6, right? If there's 2 of these and 3 of these, that would be 6 oxygens. Let me put a 3 there, and that would be 6. And I guess I'd have to put a 2 out here, right? Because I can't put a coefficient in the middle of a chemical. The coefficient, like I said, applies to the whole chemical. That would mean 6 oxygens. So now we're good on the oxygens, but don't forget, by putting a 2 there, we're kind of playing this game where we have to wiggle around, right? It applies to both, and so we're getting there because now the oxygens are good, and we were able to fix the irons pretty quickly. Let me take out my eraser. What if I were to change that 2 into a 4? Well, then this wouldn't be 2, now it would be 4. So now we have 4 irons and 4 irons and 6 oxygens and 6 oxygens. This equation is now balanced. And this shows our ratio of how these chemicals would interact to satisfy our conservation of matter. So in general, that's the process. It's a little bit of guessing and checking. It's a little bit of maybe going back and fixing some things. But I would suggest, just pick an element and start counting and you can figure it out. So to go through these, I'll go through these three with you. Sodium, one sodium, one sodium. I see two chlorines here, so one Na and one chlorine here, so we got to fix that. I need to put a 2 out here, which means 2 sodiums, so we have to put a 2 here. And now that we check, we're balanced. As it said before, if we leave this blank, that it's assumed to be a 1. If you want to write in the 1, that's totally okay. When you get more complex with your chemical equations, you might need to start thinking about it a little differently. I prefer to think about polyatomic ions. Remember that these are the ones found on table E. I kind of group them. Instead of counting just sulfurs and oxygens, seeing as there's an oxygen in all 4 of these chemicals, I think it might be smarter to just say sulfates and nitrates. In this way, now I can see 2 nitrates, so I might have to put a 2 here. And that means 2 nitrates, 2 potassiums. Well, now the potassiums match up. Actually, now that I look at it, making that one choice squares things away. So now our balanced chemical equation, as it's written on the page, would have an order of coefficients of 1, 1, 1, 2. And then finally, I wanted to take a look at this reaction on the bottom. It's a good example of really what it means to go back and double check your work, because we're going to see something pretty strange happen. I see 4 carbons. In the case of this one, I see that there are 2 oxygens, but there's no polyatomic ions, so I'm just going to lump them together and count the total oxygens. It will end up working out in the end. It just means a little bit more math. I know there has to be a 4 here because of the carbons, which now means 8 and a total of 9 oxygens. I see that there's 10 H's here and 2 H's here, so I think I need to put a 5 here. And that would make 10. 5 more onto this, so 4 more, so 5 and 8 that would be 13. Now we're good on the C's, we're good on the H's. But here's the problem. These O's, every time I add a coefficient, I'm going to count up by 2. So I can't get to 13 by counting by 2. There's 2 ways to deal with this. I personally like the idea of making it work with a decimal, but I didn't mention this. You always have to balance a chemical equation with simplest whole number coefficients. So looking at this, we can't leave this 6.5. By putting the 6.5, we do actually balance out the chemical equation, right? 6.5 times 2 is 13. We're good on C's, H's, and O's. We're good. But to fix the problem where we have that 0.5 that I really am not going to allow as a final answer, I think the best way to solve that is to double everything. Because we can double this to 13, but we can't double one thing without doubling everything else. If I doubled at the 13, now there's 26 O's. So let me clean that up a little bit. And if I go through and double everything, I get 2, 13, 8, and 10 as my coefficients, which would mean 8 carbons, 20 hydrogens, 26 oxygens. Then we have 8 carbons, 26, right? 16 and 10 is 26, and 20 hydrogens. So we're balanced. So this whole process is a little bit guess and check, it's a little bit practice, it's a little bit pattern recognition, but in general it's just counting and going back and making sure everything is balanced. Thanks for watching.